Okay, so we're going to do two things today. We're going to talk just a little more about circuits, and then we're going to talk about capacitors. Transients, changing currents. And you're going to do an experiment with capacitors in lab this week. That does require a lab report, also due after spring break. So some preparation is useful. The circuit I want to talk about to finish our conversation about circuits is a very simple one. It just involves light bulbs. And so here is, there are two kinds of light bulbs in your kit. Did that one just burn out? No. Okay. So there's one that's round, a round one, and it's got a kind of a, as light bulb filaments go, it's got kind of a thick filament, and so it's the bright one, right? And then there's another bulb that looks a little bit different. It's a little bit, elongated, so it's kind of longer. And we refer to these as round and long bulbs in the discussions. And if the wires would stay connected, this bulb lights, and it's not quite as bright, so it's a less bright bulb. But if I put them together in a series circuit, so the wire goes from the battery to the long bulb, and then to the round bulb, and then back to the battery. Of which we have two. We see something fairly interesting. Long bulb is quite bright, and the round bulb is not bright at all. In fact, it's not lit. Now, this is odd, and it's not that it got bypassed in the circuit, because if I unscrew the bulb from the socket, actually, if I take the bulb out of the circuit, the bulb doesn't light. So this is peculiar, and I want to spend a minute thinking about this circuit and seeing if we can figure out what's going on. So so here's our circuit. We have two batteries. We have a round bulb. We have a long bulb. And so our goal is to explain why in this circuit the round bulb doesn't light, even though the long bulb lights up. So we can start by doing our usual thing. And what we're going to assume here is that the length of each filament is the same, which is probably a good assumption. They're both made of tungsten, so the mobile electron density and the mobility of a mobile electron is the same for each filament. And what's just different is the cross-sectional area. One's larger than the other, so the cross-sectional area of the round bulb is greater than the cross-sectional area of the long bulb. Now, this assumption that the mobilities are equal is not necessarily true, not quite true. I mean, it is to 0th order, but since mobility depends on temperature, and clearly in this circuit the long bulb is hot and the round bulb isn't, the mobilities might not be exactly the same, okay, but to 0th order they're the same. So we're going to start by doing our usual analysis, and we'll write a node rule. So the thing that we're focused on the bulbs. So the node rule we're going to write just says the electron current through the round bulb is equal to the electron current through the long bulb in the steady state. So we can amplify this, as we usually do in these analyses, by saying mobile electron density times the cross-sectional area of the round bulb times the mobility times the electric field in the round bulb is equal to mobile electron density, cross-sectional area, mobility, electric field in the long bulb. So we just took this and substituted in these microscopic quantities for this. And we can get a ratio of the so these things we're assuming are the same, so we can get a ratio of the electric fields. The electric field in the round bulb is equal to the ratio of the cross-sectional areas of the two things times the electric field in the long bulb. And because the cross-sectional area of the long bulb is smaller, it looks like the electric field in the round bulb is a lot smaller than the electric field in the long bulb. So we know the electric field is smaller. It's still what's going on. There must be a current through it. And so what we'd like to know is how the current through the round bulb in compare to the current through the round bulb for round bulb alone. So what we mean by this is, in this circuit where there's a round bulb and a long bulb, how does the current through the round bulb compare to the circuit where we just have the round bulb in the circuit and we saw it light? So what's your guess? Bigger, smaller, the same? So we're comparing it to that circuit. Well, one way to think about that is to say, how does the electric field in this round bulb in that circuit compare to the electric field in the round bulb in this circuit? Because current's directly proportional to the electric field. Yes?
So you're asking, how does it compare between both light bulbs?
No, I'm saying I just want to think about the round bulb, which is the one that doesn't light here. So here's our circuit with the round bulb not lit. There must be some current through this because this bulb is glowing. And the question is, how much current is there in this circuit compared to the current if I just take this long bulb out of the circuit completely and just put the round bulb in the circuit and connect the wires better. These clip leads are really annoying. You've probably discovered that by now. Okay, so how does the current in this circuit through this bulb compare to that circuit through that bulb? So which is greater, are you saying?
Round bulb.
Yeah, probably this is greater. So let's see how we're going to figure that out. So in this circuit, so round bulb alone, we can write a loop rule, loop equation. So we have 2 times the EMF of the battery minus the electric field of the round bulb alone. We'll call it R1 because it's the only thing in the circuit. L is 0, so we get ER1 is 2 EMF over L. In the 2-bulb circuit, we have a loop rule that says 2 EMF. We're making this approximation, of course, that the electric field in the connecting wires is negligibly small, so that it's not 0, but it's small enough that we can just neglect it in our analysis and get reasonable answers. So we have E round 2 L minus E long 2 L. So, we know that the electric field in the long bulb, we can invert this here. We can solve this equation. The electric field in the long bulb is AR over AL. We'll call this 2. So we can say it's 2 EMF minus the electric field in the round bulb times L minus the cross-sectional area of, the ratio of the cross-sectional area is and so if we solve this for the electric field in the round bulb here, we've got 2 EMF, and we have an E sub R times L plus that ratio. So it looks like we're going to get 2 EMF divided by L plus, oh, that's an L. We have an L here. L times 1 plus the cross-sectional area of the round bulb over the cross-sectional area of the long bulb, if I did that algebra right. So compared to this, this is a much smaller electric field because it's not just divided by L, it's divided by something that's bigger than L. And so the current is proportional to the electric field, so therefore the current through the round bulb, so current in the round bulb in this complicated circuit is less than the current in the other circuit. So does that account for it not lighting? How could that account for it not lighting? What makes a light bulb glow? Friction is kind of a lump description. Yeah. What? I'm going to
say it's like the electrons colliding with the lattice.
Yeah, the electrons colliding with the metal lattice, right? Well, if the current's lower, they're not going as fast, or there aren't as many per second colliding with the lattice. So the lattice just isn't getting very hot. And I think it probably is actually hotter than just sitting around with no current flowing through it, but it's not hot enough to make a glow that we can detect with our eyes. Yes?
I had this question because I couldn't understand it well. When it collides with the lattice, is it hitting the cores, or is it like just being, it's actually hitting?
Yeah, I mean, it's colliding with these atomic cores and transferring kinetic energy to the atomic cores so that the electron loses kinetic energy. This atom starts to vibrate more. It's in an excited vibrational state, which we learned about last semester, and therefore it can lose energy by emitting a photon. Photons are in the visible region where we can actually see them with our eyes. And some are in the infrared where we could feel it with our fingers. So it's a quantitative thing here. There obviously is current through that bulb, just not enough to get the metal hot enough that it actually glows. And that's due to the fact that the electric field in this bulb, in this series circuit, is low enough that the current through this bulb is low enough that just not enough energy is transferred to the metal lattice to make the excited enough state that it actually emits enough photons that we can see them. Yes?
What was the M and F again?
The what?
The M and the F. In the top force.
What?
Where?
This? EMF?
Yeah.
That's the work per unit charge done by the battery. So read chapter 18. So this is all one thing. It's not an E times an MF. It's just EMF, one abbreviation. Other questions? Okay. So what I want to do is show you a movie of detecting how we can actually detect charge on the surface of wires. But first I need to explain how we're doing this to you before. So the idea is this. On the circuits in you building yourselves, there certainly is charge on the surface of wires, helping make the electric field that drives the current in the wires. But those wires are super good conductors, and so we don't need very much charge because you don't need a very big electric field because the mobility is high. But you can actually build a circuit that looks like, you can build a circuit where you have to make really high electric fields. And so the circuit we're going to talk about in the movie is this. There's a power supply, and then there's some wires, and there are 4 objects that are sort of bulky looking, which are called resistors. They're made of a material, it's probably actually mostly carbon, but they're made of a material that that doesn't conduct very well. It has extremely low mobility. And so to get a current flowing in this circuit, which you won't see anything glowing because these are these just black blobs that are, to get a current we need a super big electric field in each of these big clunky resistors compared to the electric field in the wires. So we want a pattern of electric field that looks, what's that, negative. So we want a big field here, and a teeny field here, and a big field here, big field here. Okay? So we're going to get presumably to do this, we're going to get a gradient of surface charge that looks like this. So if we sort of blow this up so we can draw it big. Let's see, this end was negative, and this end was positive. Here's our power supply. Then what we're going to end up with, presumably, is a lot of negative charge here, and a lot of positive charge here. And then we need a gradient of charge to make this electric field that we need. So we were going to end up with some negative charge here, but not as much, and some positive charge here, but not as much. And then we still need a gradient across here, and it could be going to 0, or it could be a teeny amount of negative charge here and a teeny amount of positive charge here, but it should be neutral right here. Now let's see if this works. Okay, we have a lot of negative charge here and some negative charge there. Does that make an electric field in the appropriate direction? Yeah, it does, doesn't it? So we get E here. We have a lot of negative charge and maybe nothing here. That could work. Here we've got positive charge, but we have even more positive charge over here. So we're still going to get a field in the appropriate direction. And finally, lots of positive charge. So to do this, you need a really macho circuit. The circuit we're going to show you is running at 10,000 volts. So this circuit is running at 10,000 volts. The current isn't actually, because these are such poor conductors. These resistors are such poor conductors. So this is a 10 kilovolt power supply, and it's arranged in such a way that the center of it is attached to ground, which is a symbol like this. So it's that grounding wire on a 3-prong plug, right, that goes down into the ground, which means that this is at a potential of plus 5,000 volts with respect to ground, and this is at a potential of minus 5,000 volts with respect to ground. And as soon as the projector warms up, I hadn't realized it wasn't on. We'll see if we can actually play. There we go. If we can actually play this video.
In a 10,000 volt circuit, there is so much surface charge to provide the large fields in many volts per meter that the buildup of surface charge is large enough to show mechanical effects. Here's a 10,000 volt power supply hooked up in such a way as to apply plus 5,000 volts to the right end of this resistor chain and minus 5,000 volts to the other end. So there's a 10,000 volt potential difference along this 4 resistor chain. In such a circuit, the amount of surface charge is enough to illustrate mechanical effects on a metal foil brought near the wire. We're going to raise the potential difference on this power supply to 10,000 volts, applying plus 5,000 volts to the right end of the resistor chain and minus 5,000 to the left end. The symmetrical arrangement means that the center of the resistor chain is at 0 volts, and we expect the surface charge to be distributed positive on the right, 0 in the middle, negative on the left. We bring a hanging metal foil near the negative end of the resistor chain. It polarizes, is attracted toward the metal, makes contact, picks up negative charge, and is repelled. Do it again. Each time we do this, we touch the foil to distribute charge over our body to make sure that the foil is nearly neutral. And bring it near the wire, polarizes, attracts, charges by contact, and is repelled. We expect it to be charged negatively, and when we bring a negatively charged pen nearby, we see that it in fact repels a metal foil. So here we're seeing a mechanical effect of the charge on the surface of the wire that builds up in this high voltage circuit. At the right end of the wire, we expect similar effects, but with the opposite sign of the charge. Here there should be a large positive surface charge buildup. We should again see the foil attracted. It gets charged by contact and is repelled. If we bring a negative pin, it in fact attracts the foil. If we take it to the center of the resistor chain, there we expect the distribution of the surface charge to be essentially zero, because the surface charge is going from positive to less positive to zero to negative to more negative. So here in the center of the circuit, indeed we see nothing happening to the metal foil. So in an ordinary low voltage circuit, the amount of charge buildup to make the small fields is insufficient to see much. But here we can see mechanical effects.
So that you can actually see that. That's on matterandinteractions.org if you want to go look at it again. But it's interesting that we actually can detect surface charge on the wire just with electrostatic means if we get enough charge on the wires. So that was the key thing. Do not try this at home. You notice these were bare wires, not because we needed to let the foil touch the bare wire. You do not want to touch the bare wire.
Maybe it's stressful that he was wearing a metal ring.
I think he had his hand in his pocket, actually, the other hand.
Well, it does show it. It shows it in video, but it's away from.
Yeah, it wasn't near the wire. This is actually a hard demo to do live because the electric field with all that charge near the wire is so big that you're pretty close to ionizing the air, and in fact you get some charge just sort of boiling off the wire into the air, so eventually then it stops working. So you actually have to set this up and do it pretty quickly. Standard thing, if you come in, set up your demo, test it to make sure it's going to work, and then try to do it later in class and it doesn't work. So, but it's nice to have a movie. Okay, so comments or questions about that? All right, so today we're going to start talking about transients. And to talk about transients, we're going to talk about capacitors in circuits. Now you know what a capacitor is because we calculated the electric field of capacitors in chapter 15. But you might be surprised to learn that this object here, which you'll find in those electricity kits, is a capacitor. Now it does not look like two large plates with a gap between them, does it? This is an unusual kind of capacitor. Some of the older capacitors are indeed made of two strips of something like aluminum foil with a piece of wax paper between them, and it just rolled up to fit in a little tube. But this is actually one that uses electrolytes, so the gap is sort of at the atomic distance, which means you can get a lot of charge into this capacitor. And so we're going to be charging and discharging capacitors in various kinds of circuits. And let's see. That wire is not connected to anything. I'm going to unhook this wire so that I can connect. Here's my capacitor here. Connect another wire to the other side of the capacitor, and I haven't completed the circuit yet, so nothing's going to happen. And I have to make sure my clip leads don't touch each other. And let's see if I can get just a little bit closer here. I want you to watch what happens to the bulb when I connect this circuit. Okay, so the bulb lit. It's kind of dim, and it went out. Well, that's interesting. Let's disconnect. Now we've got a bulb and a capacitor, but no battery here, right? So let's try just hooking up this, connecting the bulb to the capacitor and see what happens. So we will do that, and the bulb lit, but it's getting dim really fast, and it's going out. So clearly that wasn't a steady state, because in a steady state currents don't change. Clearly there was a current. So what we're seeing is a very long transient, an approach, a very long transient that leads us eventually to equilibrium when nothing's happening. And so what we're going to do today is try to analyze what's going on there. So our first downloads. So first let's just be a little descriptive. And we'll talk about discharging the capacitor first, so no battery in the circuit, just because it's actually easier to think of. So we have a capacitor that's charged, we connect it to a light bulb. Which of these graphs seems to be the best representation of current versus time in that circuit? You're saying 4. The current decreased with time, right? Okay. What do you think is a good graph of... well, let's actually ask this question first. What do you think happens? We have a charged capacitor and we connect it in this circuit. What do you think happens after the circuit's connected? Okay, so the left plate starts out negative. Okay, so presumably the left plate gets less negative charges flowing off the capacitor through the bulb and onto the other plate. And so what do you think is a good graph of the charge on the left plate, the absolute value of the charge on the left plate while you're discharging it? So the amount of charge, so the absolute value of the charge, so that it starts at a positive number, okay? We said the left plate was negative. Yeah. So, well, let's think. So you said that the charge on the left plate decreased, right? It got less negative. So if we're plotting the absolute value of the charge on the left plate versus time, it's going down, isn't it, right? Yeah, so it's getting smaller and smaller. It gets to 0. So let's see if we can understand what's going on. And I have things to draw on here. So let's think about this circuit. It's just really annoying to have to draw this all in your notes. So try to draw, considering what we saw, at the little places marked X, try to draw the electron current, meaning the drift velocity of electrons there, let's say, at each of those locations marked X at 3 different times. Okay, at a time when it's only been connected for a very short time, when it's been connected for a little while, and then when it's been connected for a long time. Okay, and once you've done that, on the bottom thing, draw the electric field at each of those locations that corresponds to the drift velocity you drew, the electron drift velocity. All right, so what do your drawings look like? Okay, so if this is, well, let's make an assumption about which plate of the capacitor is negative to start with, okay? So we'll say this one's negative to start with, and this one is, that one's positive. Then, presumably, we have electrons flowing this way in the circuit, and, right? They're flowing off the negative plate through the light bulb and onto the positive plate. And therefore, the electric field has to, at each location, has to point opposite to that. So we have an electric field here like this, an electric field here like this, and an electric field here like this. So if you draw just the electric field, it might look something like that. Because then it gets smaller, right? So the current's decreasing. So we've got an electric field. So we've got, this is still negative, but not as negative. I'll draw that bigger so I can exaggerate it. So we've still got an electric field that way, but it's now smaller. And finally, when we get to this location, so let's actually draw charges here. This is very negative. Now, presumably, now notice that I've drawn the electric fields in any particular time all the same size. Why do you think it makes sense to do that? The drift velocity, so isn't the electric field proportional to drift velocity? Or the electric drift velocity is proportional to the electric field if you want to think cause and effect. But in fact, in principle, we know that the drift velocities of all these things are changing. And so maybe they're not equal at any given instant. And the reason it's reasonable to assume that they're equal at any given instant is that remember that the rearrangement of surface charge on the surface of a circuit to make an electric field that avoids charge piling up is very fast. Okay, that happens on an order of 10 to the minus 18 seconds or something. So that it is surface charge, negative charge here, and a little bit of negative charge here. Negative charge here. Now, where do we need a big electric field in this circuit? In the light bulb, right? So we haven't drawn the field in the light bulb. We're looking at the field in the wire. The light bulb has to have a really big electric field getting smaller and finally zero. So we're going to have surface charge building up here to make a big gradient of surface charge across the light bulb to make the light bulb light. But we're in something that is sometimes called a quasi-steady state, which is it's not really a steady state because over some time, like 10 seconds, it's changing. But at any instant, currents everywhere are roughly equal. Now so does that make sense? So why does the capacitor discharge? Aren't the electrons on the negative plate attracted to the positive plate? Don't they just want to stay there? So that's a problem, right? I mean, the electrons are attracted on the negative plate, are attracted to the efficiency of negative charge on the positive plate. So why would it ever discharge? We saw that it did. And to think about that, we actually have to go back to this caveat that when we think about a circuit, we have to think about the whole circuit and not just one piece of it. So let's actually think about, so here are our negative charges, here are positive charges. Let's think about the wire, okay, because these electrons are attracted to those positive charges. Why don't they just jump across? There's an insulator in between, which could be air, or it could be some other insulator. So in fact, there's no conducting path there. So they can't just jump across. But let's look inside the wire. Here are all these negative charges here, and there are indeed positive charges here. But they're a little bit different distances away, and so we really are going to get an electric field inside the wire that way. What's going to happen to an electron here inside the wire? Yeah, it's going to go this way, isn't it? At that point, we now have electrons flowing away from the negative plate. And if electrons didn't flow off here, we'd get a big positive charge in the middle of the wire. So electrons now flow off the plate because they're attracted to where the other. Likewise over here, we have an electric field. The positive charges are a little closer than the negative charges. So we have an electric field that way. And so any electron in the wire is going to want to flow onto that. Now this would happen a little bit even if the wires weren't connected. So we'd get a very short situation where, suppose we had wires that just ended like that. For a very short time, we'd have electrons flowing this way a little bit and electrons that way, but then we'd start building up negative charge here, and we'd start building up positive charge here, and the electric fields would change and it would come back to equilibrium. But if we actually make a conducting path where we let the electrons go all the way around, now we can actually have a current flowing through the entire wire and eventually discharging the capacitor. So remember that we had to look not just at these electrons, but everywhere else in the circuit to figure out what was going to happen. Okay, what about charging? Turn the page over. So same thing, in the top, draw, first of all, at the x-axis, just the electron current. So we're starting with a capacitor that has no charge on the plates at all, right? So draw the electron current, a tenth of a second after connecting the circuit, and then a second after connecting the circuit, and 100 seconds after connecting the circuit. And then on the bottom one, draw appropriate charge and field distributions that actually correspond to this. So the end of the battery with the knob is the positive end, and the end with without the knob is the negative end. So that's in this diagram, that's negative, and that's okay, so what do we have here for the initial situation? So at t is 0.1 of a second, or maybe even 100th of a second. And we saw that when we made the connection, the current flowed right away, right? So what do we got for drift speed, say, here? Electron current is flowing away from the negative end, right? So we're going to have, and that means electron current here is flowing that way, and we have electron current flowing that way. So the electric field must be opposite. So we must have an electric field here that looks like that, and an electric field here that looks like that, and an electric field here that looks like that. How much charge should I draw on the capacitor here? Yeah, pretty much none, right? Because it was initially uncharged, which is interesting because that says that the electric field here and here and here are due only to the batteries and the charge on the surface of the wire, and the capacitor is making a zero contribution. Well, what happens when it's 1 second? Is that what the second one was? 1 second. Okay, so now what's happened after a second? We have some charge on the capacitor, right? So which sign is the charge here? Negative, right? So we have a little bit of negative charge, and we have a deficiency of negative charge here. And that means that the electric field at this location is now due not only to the batteries in charge on the surface of the wire, but it's also due to the capacitor. And so we have an electric field here due to the batteries and the surface charge, but we have an electric field here due to the capacitor, and so the net field here got smaller. As the capacitor charges, the field outside the capacitor, which is technically called the fringe field of a capacitor, is increasing. And so E net is just smaller. So we have a smaller net electric field at these locations. And therefore, the drift speed of electrons is lower at each place, and we've got a smaller current. And that makes sense because the bulb wasn't as bright. So what happens at the very end? What should the drawing look like at the end? So what do I draw here? Lots of negative charge. Lots of positive charge. What's the net electric field here? 0. And that's the sum of the field due to the capacitor and the field due to the batteries plus surface charge. And it's also 0 here, and it's also 0 there, right? Okay, so which graph shows current versus time while we're charging? So we hook it up, it runs. Okay, I'm seeing a disagreement here. I'm seeing 2 and 4. So some people think it's 2, some people think it's 4. So let's think about what we would have observed if 2 was correct. When we hook up, we first connect the circuit, the light bulb is out because there's no current, and then it gets brighter and brighter and finally reaches a constant brightness. Is that what we saw? Definitely not. We saw the light bulb start out bright and get dimmer and dimmer and dimmer, so it's definitely 4. That's the correct answer. What happens when we first connect it? Yep, yep. So electrons pile up on the left plate, right? They can't jump across because, as Nick pointed out, there's no conducting path there. The magnitude of the charge on the right plate while we're charging it versus time. Yeah, yeah, yeah. That finally we get to say 2, right? Yeah. So finally there's something that does build up as we charge until we reach a point where there's enough charge to make the net field 0 in the circuit and current stops flowing. So we sort of have this long, extended transient. So you'll have a chance to experiment with capacitors this week in lab and to build some of these circuits. An interesting circuit to build, which is not actually part of the lab, and you have to collaborate with another group to get 2 capacitors. But here's an interesting circuit to build. So we put a capacitor here. We put another capacitor here, so we put 2 capacitors in the circuit. And the question is the light bulb going to light or not? So I'm seeing people saying yes, I'm seeing people saying no. Okay, so try it in lab, all right? Just take a minute and try it in lab and see what happens. Now, yeah, I mean, it's an interesting one to think through, isn't it? Now, capacitors have markings on them which tell you something about the capacitor. And a question that we might ask is, does a capacitor have a fixed ability to store charge? So what would happen if we put if we made a circuit with a light bulb and a capacitor and one battery versus a light bulb and a capacitor and 2 batteries? Would the capacitor have the same amount of charge on it? And one way to think about it is to think about equilibrium, and we've gotten to the point where there's no current running. So let's take equilibrium, and let's write a loop equation for this circuit. So we have, let's go this way, so we have the EMF of the battery. The connecting wire is negligible. We have the potential difference across the capacitor. And then we have the electric field in the bulb times the length of the filament, and that's equal to 0. Now, in this equation at equilibrium, is any term 0? Is the EMF the battery 0? No. Potential difference across the capacitor, well, that's probably not 0 because now we have charge on the capacitor. What about the electric field in the light bulb? At equilibrium, what's the electric field in this light bulb? 0, because if it weren't, you'd have charge flowing, so that's 0. So we have the potential difference across the capacitor has to be numerically equal to the EMF of the batteries. And there's, whereas in this case, we'd have a 2 EMF minus the potential difference across the capacitor minus E bulb times L is 0, that's that. So we get the potential difference across the capacitor is equal to 2 EMF. There's a marking on the capacitor which is called it, and its capacitance, we've run out of letters again, so capacitance is capital C. Its units are farads. And what is capacitance? Well, the amount of charge on a capacitor is equal to the capacitance of the capacitor times the potential difference across the capacitor. And this is a, these are all positive numbers here, so the amount of charge on the positive plate of the capacitor, if you will. And so it looks like capacitance has to be the ratio of the amount of charge on one plate to the potential difference. And so it looks like its units have to be Coulomb per volt, and that's 1 farad. So this capacitor actually says that its capacitance is 1 farad. So let's figure out how much charge there was on this capacitor when I hooked it up to 2 batteries. Okay, and let the light bulb at 2 batteries. So we have that circuit there. So Q would be equal to batteries, would be equal to C delta V, so 1 farad times 3 volts. It looks like 3 coulombs. That's a huge amount of charge. That's an insane amount of charge. Now these are very unusual capacitors, actually. They're sometimes called supercaps. Most of the capacitors that you'd see in ordinary circuits have capacitances of something like 1 microfarad. And so if it was 1 microfarad, we'd have Q would be 1 times 10 to the minus 6 farads times 3 volts, which would give us a microcoulomb, which is what you're going to get in ordinary circuits. These are actually made as, what?
3 by 10 glasses.
3, oh, that's true. 3 times 1 is not actually 1. 1, 3, they're all the same, right?
The one on my bag is 1,000 micro. Something like the half. Oh, well, okay, that makes sense now.
So 1,000 microfarads would be a millifarad, right? So that would be, so 1,000 microfarads is 1 millifarad is 1 times 10 to the minus third farad. So you get what? A millicoulomb. Yeah. Is there a maximum charge that this capacitor can hold? At a certain point with a capacitor, if the electric field gets big enough, you know, insulators become conductors. Air ionizes, or insulating substances start to break down. So for any capacitor, there is a maximum charge you should try to put on it. This capacitor actually says it's 1 farad, and it also says 2.5 volts, which suggests that that's the maximum potential difference you want across the capacitor. Now we're putting 3, and that's okay. I wouldn't do 6. I wouldn't even do 4.5. Okay, but 3 is reasonable. So for the ones we're using here. Questions about capacitors? Okay, so next time what we're going to do is, so in recitation we'll do some capacitor things, and we'll also do some review problems involving potential difference in magnetic field. And next Thursday, what we're going to do is, this is our first, by defining capacitance, this is our first step into the world of meters and resistors and the terminology that we use with ordinary circuits. So next time we'll continue with that and sort of translate our micro view of circuits into the view that you'll mostly find on circuit diagrams and discussions of circuits. So that's what's happening next time.